Okay, hi, Assalamualaikum and hello everyone. My name is Nur Siti Khadijah Aruna and I am from UiTM Johor. Okay, today we will going through some important terminologies that we might pass through while solving proving question in this chapter. Not only in a forward-backward process and construction method, will use the terminology in any other method that you learn in this chapter. So as an introduction, the definition in mathematics are just like an agreement that has been agreed by all parties to the meaning of particular term. Okay, so for example, the statement A implies B. This is what you have learned before. So statement A implies B was defined as true in all cases except for A is true and B is false. This is what you learn in a truth table. If we have A implies B, this statement will be only false if A is true and B is false. Other cases, it will be true statement. Okay, but why did all mathematicians agree on this definition? Why? So it is simply because these definitions are not made randomly. Usually definitions are made and agreeable since it is supported by a related mathematical concept. Okay, so basically the definition have been proved before by some other mathematician and with supported mathematical concept. Okay, here's some definition that might be important to chapter 3. So what is the definition? The first is divide an integer n divide an integer m, written as n divide m if m equal to kn for some integer k. Here the unknown k or variable k have to be declared as integer. So secondly is prime. We have isosceles definition, equal, even and odd. Even and odd we have discussed in the video before this. So rational number, we have definition of rational number and equivalent and or subset, upper bound, convex function and convex set. So this is some of the definition that you might come across while solving in this chapter, proving question in this chapter. So we have a lot more definition than you think, but these are what we usually use. You might see some other definition as you do a lot more exercises in different method of proving, not only in this two method, forward, backward and construction. So mathematical terminology, there are four terms that will always come across us in dealing with proof or reading the papers, the research paper, which is a proposition, theorem, lemma and corollary. So what are all these? The proposition are the true statement of interest that you are trying to prove. Something that you are trying to prove is proposition. Theorem come from proposition that are considered to be extremely important. Okay, so lemma is also come from proposition that is used in a proof of theorem. So if a proposition used in proving the theorem, we call it lemma. So corollary is a certain proposition that follow almost immediately as a result of knowing that the theorem is true. Okay, so proposition is corollary is also come from the proposition. Okay, so we're going to the next part, which is construction method. So as an introduction, this method will work with existential quantifier that you have learned in the chapter before, chapter 2, or you will be dealing with the word there is, or there are, or there is exists. Okay, so some other words that come with the same meaning with the existential quantifier. So for example, in definition of rational number, we have a real number R is rational if and only if there are, this is the existential quantifier, integers P and Q with Q not equal to 0 such that R equal to P over Q. So in this definition, rational number can be expressed as a ratio of two integers, which is R equal to P and Q, two integer which is P and Q, ratio of this integer. How do we know that P and Q is integer? It is clearly stated here, integer P and Q. Okay, in which the denominator is not 0. So in the ratio, the denominator might not equal to 0. Okay, so the next part is, another example is the definition of even integer, which is an integer n is even if and only if there is existential quantifier, an integer k such that n equal to 2k, so integer k. When deal with this kind of proving, we must carefully include the existential quantifier. We must include the existential quantifier. For example, if defining even integer, full statement must be included in the existential quantifier such that there is an integer k such that n equal to 2k. Symbol k must be defined clearly in the process. So if you're adding some variable or unknown, you must define clearly in the process. So each time existential quantifier appear in the statement, we will have a standard form of there is an object with a certain property such that something happened. Okay, as we prove A implies B, A implies B is true, construction method is applied if existential quantifier found in the forward process. So we found an existential quantifier in the forward process A or A1. So it doesn't state that if you found existential quantifier also in a backward process, it doesn't state that. That is not a construction method. Okay, so you might found existential quantifier in both forward and backward process, doesn't matter. So to illustrate the quantifier, there is in the standard form, A is there is an object with a certain property such that something happened. The proof must consist of showing that the object has the certain property and satisfied something that happened. So what if you found the existential quantifier also in the backward process? So the idea of this method is to construct on the desired object. So if you get existential quantifier also in the backward process, the constructed object will still become a new statement in the forward process. So don't worry. For example, identify and write each of the component. There is an integer p greater than 2 such that p square minus 5p plus 6 is equal to 0. So this is the existential quantifier. There is an object. Object is integer p. This is the object. So this is the certain property, p is greater than 2, such that this is something happened. Let's see the answer. So the object is integer p, the certain property is p greater than 2, and something happened is p square minus 5p plus 6 equal to 0. Okay, another example is proved by using the construction method. Okay, we're going to prove this question by using construction method. So if s and t are rational number, then s plus t is a rational number. So in this question, we didn't see any existential quantifier, but the question asks us to prove in construction method. Okay, your answer should have an analysis of the proof and the condensed proof. So let's see. So we have statement A and B, which is A is S and T are rational number, and B is S plus T is a rational number. So let's see. We might use some definition here, which is definition of a rational number. So we're going to declare the statement B1 using the definition. Here, a real number R is a rational number if and only if R can be expressed as a the ratio of two integer, which is P and Q, in which the denominator Q is not 0. So basically it is P over Q, and Q is not 0. P and Q must be declared as integer. Okay, so statement B1, there is an integer P and Q not equal to 0, such that S plus T equal to P over Q not equal to 0. So there is an existential quantifier here, but do not worry, we will use the quantifier, the constructed object will still become a new statement in the forward process. So let's see the forward process first. So from A we have there is an integer R S T U and S and U not equal to 0, such that S equal to R and R over S. This is the uppercase of S, this is the smaller case of S, and this is a smaller case of S come from the denominator, and T equal to T over U not equal to 0. This is uppercase T and this is lowercase t. So this is what I mean when we say that the constructed object will still be in the forward process. So we construct S plus T from statement B, but using the information in A1. It must be linked in the forward process. Okay, so S plus T is equal to R over S plus T over U. So simplifying this, you got RU plus ST over SU, which is, from here we got S not equal to 0 and U not equal to 0, thus SU will not equal to 0 because S not equal to 0 and U not equal to 0. We stated it here. So P, it will equal to P over Q, Q not equal to 0. Why we have this statement? This statement is come from backward process here, which is S plus T or equal to P over Q, Q not equal to 0. So this RU plus ST over SU will equal to P over Q if P is equal to RU plus ST, if this equal to P and this equal to Q. So this statement will equal to P over Q, and Q not equal to 0. Are we sure that Q not equal to 0? Yes, it is, because Q come from SU, which is S not equal to 0 and U not equal to 0. So Q equal to SU and Q not equal to 0. So this statement same as B1. So we finish our proving here. So as the condensed proof, you can read it from here, from the hypothesis, what we have, and you will be explained one by one from A1, A2, and the conclusion. Okay, so basically that is all how you want to prove with construction method. So thank you. And if you have any question, any information you want to tell me, please email me at the email given. Thank you. Assalamualaikum and have a nice day.